Okay, let's go ahead and get started with a slightly different charge distribution problem. So notice point P is in a different spot. It's still well defined, but it's in a different place than we have seen before. And take a moment and think about what the direction of E is going to be at point P. So you should be able to figure out conceptually what quadrant E is going to be in. The first thing I will do here is I'll draw in my DE due to my DQ. So as I look at your diagram in your work, your DQ and your DE should always relate to each other. Oh, and I'm in wrong mode here. Your DQ and DE should always relate to each other. So my DE, here's my point P up here. And my DE is going to be here in this direction. Yep. I'll draw in my R too. R is always the distance from my source charge to my point of interest. So this here is R. And my A is, of course, just this distance here, the distance that point P is away from the end of the rod. All right, notice that DQ also has some length to it that in this case I'm going to call dy since it's along the vertical. And I'm going to put in a coordinate system here where I will have positive y upward and positive x rightward. And that puts the origin, or just I'm going to make super clear here that I'm saying that the origin is right here. That's my 0, 0 right there. All right. So now I'm kind of ready to do this. I need to think about DE in terms of components. So just so you can kind of start having that in your mind, let's go ahead and define some things as we're getting started. The same that we always do, right? We always need to define DQ. And in this case, I can use lambda dy, as you've seen in these line charge problems before. I need to also define R. And in doing that, I'm going to label my Y on my diagram because I'm going to be defining it in terms of Y in this case. So Y is from the origin to my differential element. That's my Y. So Y changes, of course. So I'll define my R then now that I'm remembering what my Y is, right? So R is going to then just be the square root of a squared plus y squared. Okay, fairly straightforward. We see that as our DQ moves around, R varies because Y varies. Okay, and then I know that I need to split that DE up into components, and I know that there's going to be a Y component. Every DE is going to have a Y component and an X component. I can think about that as I'm moving along the rod. I guess the very, very end of the rod here will only have a horizontal component because there'll be no vertical component for that one. So this is, I can label as DEY. And this down here is, of course, DEX, my X component there. I'm going to label some angles or an angle in here so I can express these vectors. I'm going to call this angle phi, and that's the same, of course, as this angle down there. So the next question we always ask ourselves here after defining DQ and R is to express the surviving component. So take a moment and ask yourself if there's any cancellation in this problem. Move that DQ around and see, is there any cancellation in this problem? And the correct answer is no, we don't have cancellation. So that's kind of cool. What we do have, though, is we have to stop and think about the fact that we need to express the X and Y components of this electric field separately. The problem is if we just kind of plow on and don't think about direction here and just set up an integral and like force it, what's going to happen is the integral doesn't know that this is a vector, so it's going to sum all the X and Y components together or all the DEs together as if they were not vectors. It's not going to know to use like vector arithmetic, right? There's no way it would know. So we have to do that. Just like how we have to express the surviving component, here, what we must do is to express our E in terms of the individual components. So a way that I can think about that just sort of in broad strokes is that my E field here is going to be the integral of dE sub x here plus, that's I hat, sorry, plus the integral of dE sub y j hat. So that's where I'm going, right? That's what I want to try to figure out. And I know that I can express my dEx, right? If I, now that I have that phi defined as dE, so look at your x there, it's going to be sine phi, and dEy is going to be dE cosine phi. Okay, great. So sine phi and cosine phi, let's take just a moment and jot those down because we like to have those for later. So look at your triangle here. Your sine phi is going to be A over R, and your cosine phi is going to be Y over R. And of course, we have our R defined here, and we have our dq defined there. So we're probably all ready to write out our integral then at this point. So I'm going to start with the x component first. So e sub x is going to be equal to the integral of dE sine phi. So let me write that out. dE is, of course, k dq, so that's lambda dy for us, right? Over r squared. I'm just going to leave that as r for just the moment, times sine phi, so that's going to be times a over r. So what that does is it changes the square to a cube. Okay, so now I can start thinking about expressing this in terms of y and starting to formalize it a little bit. And I can pull my constant stuff out in front. So that's going to be k lambda a, yeah, dy over r cubed. So that's going to be dy over a squared plus y squared to the 3/2 power. So r is under a root, remember? So if I cube that, I get 3/2 power. And the bounds of this integral is going to go, remember, we always go low to high here. And notice where I've put my origin and my positive y. So here I'm actually going to be integrating from negative L to 0. Okay, so that's my x component setup. Let's do our y component setup. Of course, you'd still have to execute the integral and evaluate the integral and then write this all in vector notation, and all that is done in the written solutions. What I want to try to do in these videos is to connect you to the concept as much as I can. So my y component is here, e sub y. That's going to be, now I'm looking at dE cosine phi. If I add up together all the dE cosine phis, that's going to give me the y component of my electric field. And I can see that those are all pointing upward. Just like the x component contributions, the dE sine phis, those directionally were all pointing rightward. So this problem is really straightforward as far as direction is concerned. dE cosine phi, so that's going to give me my dE is k times dq, which we're writing as lambda dy. Over r squared, and I multiply that by cosine phi. Cosine phi is y over r. So again, this r squared becomes an r cubed there. So let's rewrite this a little more technically. I'll pull out the constant stuff. So k and lambda come out front. And now I'm left with a y dy in the numerator. Y is a variable, so that's got to stay in there. And then r cubed in the denominator. So that'll be a squared plus y squared to the 3/2 power. And again, I'm in both cases, I'm integrating with respect to y, negative L to 0 there. And then, so these next steps here for these integration forms, you can feel free to use the integral table. As I mentioned at the beginning of the quarter, the integral table that is posted in Canvas for you, that is the table that will be made available to you for the next exam where you're working with these charge distributions.